door. Does anybody know what a douchebag actually is?
My ex-husband.
In the olden days, they had, did you ever see an old-fashioned hot water bag? It's like a red rubber bag, and you would fill it with hot water, and then on a cold night, you could put it in your bed sheets, or you could hold it if you had tummy cramps. It'd be, the warm water would, you know. Well, a douchebag was essentially the same thing. It was a red rubber bag, and it had a hole in it, so you could hang it up in the shower, and you fill it up with water, and then there's different solutions you can buy, or you can put vinegar in it, or whatever you're gonna douche with, you know. And then it had like a long hose coming with like a spout at the end with holes in the spout. So as soon as you hung that bag up, the water's gonna start running through the hose and out the spout. Then you insert it, and it get a little shower on the inside. That's an old-fashioned douchebag. And then, with modern technology, they invented these like squeezy bottle things like Summer's Eve, where the solution is in a plastic bottle, and then it's got a spout on it with holes in it, and you stick it up in there, and you just squeeze the bottle, and the solution comes out the holes and rinses you out from there. Yeah, it's like a vaginal enema, yeah.
How can they do that?
Huh?
How can they market something like that if it's going to have adverse effects, if it's going to change your
We market
pH?
all kinds of stuff that has adverse effects, like
Oh, that's
candy, soda. If people will buy it, they'll sell it. But it's just kind of misleading. They advertise it like all women have this major problem and it must be fixed with this product. It's like probably a rare occasion when you have some kind of a problem, and that's probably not going to fix your problem, at least not permanently, maybe temporarily. All right. One of the augers we're going to use is McConkie auger. We'll come back to that. But it wouldn't hurt you to start looking. Here's just an example of different kinds of augers. I actually want to do the growth curve. That's where we're going to. Okay. Just to walk you through these, because by the end of the week I want to have this whole thing done. Remember we talked about anaerobic bacteria? You have to grow them in a special kind of a hood where there's no oxygen. It sucks out the oxygen. So, but before they had special hoods, we do it in a thing called a candle jar. And so here you've got chemicals to eliminate the oxygen in the air. But before that, they literally used a big dome, put a candle underneath there, and when you put the dome over it, once the candle, the flame used up all the oxygen, it would go out and you created an oxygen-free environment. So which kind of bacteria are anaerobic? The ones that we're talking about? Clostridium, gangrene, tetanus, and why do they cause disease in puncture wounds? Because deep wounds are anaerobic environment. Just the right environment for gangrene and tetanus and botulism even. They like anaerobic environment. That's why botulism can be a poisoner of canned foods. Yeah, I wanted to tell you about Barbara Friedman. If we have time, I'll do that.
So is that where the hyperbaric chamber comes in?
Hyperbaric is extra oxygen pressure. So if gangrene hates oxygen, you put your patient in a room with extra oxygen pressure, that kind of kills the bacteria and keeps them from spreading. Exactly. So a hyperbaric chamber, you would be treating anaerobic bacteria, trying to get rid of them. Okay, we already talked about binary fission, which I call transverse binary fission. Here's that septum, transverse plate is what I call it, right? And that's just a recap of binary fission. Here's your parent cell. It replicates its nucleoid as it elongates. Then the transverse plate or cross wall or septum or whatever they want to call it starts to grow. While this is happening, the cell has to be manufacturing peptidoglycan and making the cell wall so it can create that transverse plate. If you take penicillin and certain antibiotics are going to interfere with the bacteria's ability to make peptidoglycan and make that wall. Okay, in this case, there's no penicillin involved, so there's a completed septum, and it separates into two daughter cells. What this is showing is the next generation now. This cell will replicate, and this cell will replicate, and then I'll have 4 cells. And 4 cells are gonna make 8 cells, and 8 cells are gonna make 16 cells, and so on and so on and so on. So, let's see if we can crank this out by 3:30. Alrighty. 1 cell replicates, makes 2 cells, right? Now, when you're working with your bacteria upstairs and you take a little sample, do you ever have 1 cell? No. Even when you streak your plate from the broth, say, you're separating into CFUs, you really don't know how many bacteria you're putting on the plate because you can't see anything because they're so freaking small. But you're hoping that there are some bacteria there, and you're hoping that your streak plate method is good enough to separate at least some of them out into individual CFUs. So you might think of 1 cell as 1 colony forming unit. And in one of the experiments we do, that's what we're going to do. We're going to go back and look at plaque forming units. We're going to look at colony forming units. We're going to try to calculate how many we started with. But at any rate, if you have 1 cell, it's going to divide into 2. 2 are going to divide into 4. 4 are going to divide into 8. 8's going to divide into 16. 16 is going to divide into 32. Woohoo, and so on, 64, right? So, 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, because 2 times 2 times 2 is 8. 2 to the fourth, 2 to the fifth up here, 2 to the sixth. Did I do that right? Got any good mathematicians handy? Okay. This is exponential growth. That's how bacteria divide and grow, exponentially. So the process of transverse binary fission is a doubling. So every generation you're going to double, double, double. First generation, second generation, third generation. There is an appendix in the back of your book if you like math challenges.
No, thank you.
It teaches you how to calculate the generation time of different types of bacteria. There's a formula in there. Okay, so this is called a logarithm. Remember log? Logarithm. Rhythm. Logarithm. I'm missing a letter. What letter am I missing? H? Logarithm?
Yeah.
Okay. Or an exponent. So bacterial population growth, how your CFU grows into a colony, is exponential growth. So bacterial replication or bacterial population growth is logarithmic or exponential. Population growth is logarithmic or exponential. Now, bacteria like E. coli can replicate every 20 minutes. So if a new generation is every 20 minutes, within a day, you can actually get a visible colony on your Petri plate. Staphylococcus well, most Staphylococcus, I think, about 30 minutes replication. So, some bacteria, however, are very slow. Guess who's a very slow grower? Mycobacterium. Depending on the sources that you read, it'll tell you they take them like a week to grow. 2 weeks to get a visible colony on a Petri plate. So the slowest growers are like Mycobacterium, quick grower, E. coli. But most bacteria will replicate in about 30 minutes. E. coli is a little faster, 20 minutes. So if the E. coli in my bowels is replicating every 20 minutes, how come I haven't exploded yet? How come my bowels haven't burst? Because some of the older ones are dying, right? New ones are being made, but older ones are dying. Also, they have competition from other microbes in my bowels. The E. coli is not gonna be able to grow and take over if there's others in there that are like, hey, I need some space and nutrients too, so you just back off. So there's competition from your other normal flora, and let's not forget the immune system keeps everything in balance. So the balance is maintained by your immune system. If there's too many E. coli, you're gonna have competition from other normal flora, and your immune system might actually start to go after some to keep the balance. But your normal flora themselves are part of your immune system. Why sometimes it doesn't want to change slides? I don't know. Clicking doesn't go anywhere. So this just compares arithmetic growth to exponential growth, right? If the world was a perfect world and there was enough resources, no matter how many people or how many bacteria, the exponential growth would go to infinity. But that's not real. We're eventually going to run out of resources, space, oxygen if it's needed, and we're going to accumulate wastes, which are going to kill us off. So, this shows you how to plot logarithmic growth. If you plot the number of cells, suppose I asked you to count how many bacterial cells were on your Petri plate. You think you could do it?
No.
And if you could do it, you would need a really big graph to plot them, because you'd have like billions of cells, right? So this is kind of impractical. So instead what we plot is the logarithmic number, the log number of cells. And when you do that, instead of having sort of a curved line, it might straighten out your line.